Hello everyone, welcome back to my YouTube channel. Today we are going to study the overview of point defects and the derivation of equilibrium concentration of mono vacancies. So let us begin with point defects. So what are defects basically? Defects are actually any kind of discontinuities in the crystalline array. So any kind of discontinuity in the otherwise periodic or crystalline array. Okay. So point defects are actually zero-dimensional defects. Point defects are 0D defects. And then let us see the various types. They are vacancy defects, when the atom is missing from its lattice position, impurity, some foreign atom is present within the crystal. Third is Frankel defect, which is the presence of an interstitial lattice atom at the interstitial site. So it is presence of a lattice atom at the interstitial site. That is a site which is actually not a lattice position but lies within the crystal structure. Next is Schottky defect. This is basically the missing pair of positive and negative ions from the lattice positions. This is missing pair of positive and negative ion from the lattice positions. So why both positive and negative ions are missing? To maintain the charge neutrality of the crystal. To maintain the charge neutrality. That is, charge should remain unchanged. Okay. Other is interstitials. As the name suggests, they are the presence of atoms at the interstitial sites and then anti-sites. So, point defects are actually thermodynamically stable defects. We'll see that in a while how. So, in very simple terms, we can say that they're thermodynamically stable because introduction of point defects into a system actually lowers its energy, and lower the energy, the higher will be the stability. So let us define point defect in detail, or more technically. So it can be defined as vacancy or a mono vacancy, that is missing of a single atom only. Mono means one. So they are imperfect point-like regions in a crystal. And this region extends only up to approximately 1 to 2 atomic diameters. Okay? But this is just the imperfection range of that ranges goes up to only 1 to 2 atomic diameters. But the distortion field that is created because of these imperfections, distortion field that can extend up to very large distances. So its effect can be seen at distance as high as 10 to 20 atomic diameters as well, or even more. Okay, so let us see how these point defects are generated. So this is just an overview. We can go in detail about each one of them in a later video. So there are two kinds of processes. One is equilibrium process. Another is non-equilibrium processes. Okay, so now within this there are multiple other processes. So let us see the equilibrium process first, that is slow heating. This is slow heating. Since the defects are in thermal equilibrium at a particular temperature, so at that temperature concentration of defects we achieve is basically equivalent to the equilibrium concentration of defects, since it is a slow heating process. Okay, now in non-equilibrium processes equilibrium is not maintained, so concentration of defects is actually not equal to the equilibrium concentration. This is the main difference between the two processes. Okay, so now the different types of non-equilibrium processes are crystal growth, quenching, that is very rapid cooling from a high temperature to a low temperature, then plastic deformation, then irradiation by electron or neutron or protons, so this would lead to ejection of atoms from the crystal system. So when high energy electron, neutron or proton bombards the crystal, so certain atoms are ejected out. So that is the generation of point defects. Then we have oxidation of silicon. that injects certain interstitial atoms. And these interstitials are again point defects, and nitridation of silicon injects vacancies. Okay, so let us now see how much energy is required to form a vacancy. Energy of vacancy formation. So here by vacancy we mean a mono vacancy. Okay, so Gibbs free energy is enthalpy of formation for one vacancy minus T and entropy of formation. So here this is the entropy of formation and not the entropy of mixing. Okay, so N is the number of vacancies or mono vacancy, whereas capital N is the number of lattice sites. Okay, so change in Gibbs free energy will be given by Gn minus G naught, where this one is after the formation of n vacancies, and this is after the formation of n vacancies this is when there are no vacancies, 0 vacancies. Okay, so delta Gn is given by delta HF for n vacancies minus T delta S mixing. Now enthalpy of formation of n vacancies can be linearly related to the enthalpy of formation of one vacancy, so it will be n times the enthalpy of formation of one vacancy. And it's not the change, it's the enthalpy of formation. Okay, so this is the change in enthalpy for formation of one vacancy. Okay, so next is, and this delta S mixing is delta S thermal plus delta S configurational. So delta S thermal is approximately 0 since we assume ideal mixing, so no thermal effects are involved for mixing, whereas delta S configuration is not 0 because the vacancy can arrange in multiple ways. So this is equation 1, this is 2, and this is 3. So now configurational entropy for n vacancies is given as S configurational of n is equals to k kb ln omega. This is the Boltzmann constant. And this omega is basically the thermodynamic probability of distributing n vacancies at n plus capital N sites. Okay, so this omega can then be written as n plus small n factorial divided by capital N factorial into small n factorial. So this equation is 4, this is 5. Now let us see initial configuration entropy. Initial configurational entropy without any vacancy. Okay, when there are no vacancies present, so what is the configurational entropy? So since there are no vacancies present, n is equals to 0, so omega becomes capital N factorial by capital N factorial into 0 factorial. So this is 1, so omega is 1. There is one single perfect arrangement. So S initial for 0 vacancies become k ln 1. So ln 1 is 0, so initial entropy is 0. This is equation 6. So what is the change in entropy now? When n vacancies are created, it is delta S configurational is equals to S configurational n minus S initial for 0 vacancies, and this is 0. So we are left with delta S configurational is equals to k ln omega. So delta S configurational is equals to k ln n plus small n factorial divided by capital N factorial into small n factorial. Now we use Stirling's approximation to solve this complicated logarithmic value. So as per Stirling's approximation, ln of x factorial is equals to ln of x factorial is equals to x ln x minus x for x much larger than 1. So applying the same to our equation number 8, we get delta S configurational is equals to k ln n plus n factorial minus ln n factorial minus ln n factorial. Then applying Stirling's approximation, this becomes k n plus n ln n plus n minus n plus n, then minus n ln n minus n, then minus n ln n minus n. Okay, so now opening up the brackets, we get delta S configurational is equals to k n plus n into ln n plus n minus n plus n minus ln n plus n minus n ln n plus n. So these n's cancel out. So this they cancel out. Then we are left with delta S configurational is equals to k n plus n ln n plus n minus n ln n minus small n ln n. Okay, so now let us collect the terms together. Okay, so if we collect the capital N terms, we get capital N ln n plus n minus ln n capital N plus small n. So we get ln capital N plus small n minus ln small n. So using logarithmic rule, we get capital N into ln n plus n by n plus small n ln capital N plus small n by small n. This is what we end up having. Okay, now number of vacancies is much less than the number of lattice sites. So we can say n plus n is approximately equal to capital N only. Now using this in equation 9, we can get delta S configurational is equals to k capital N ln capital N by n plus small n ln n by n. Okay, so this becomes 1, so ln of 1 is 0, so this whole terms becomes 0. So now what we have is delta S configurational is equals to k n k ln capital N by small n. So reversing this, we get delta S configurational is equals to minus k ln small n by capital N, and this small n by capital N is x1v, that is fraction of mono vacancies. Okay, so what we can write is delta S configurational is equals to minus nk ln x1v. Okay, now let us put this value that we have got in equation 10 in equation number 1. Okay, sorry, in equation 1 and 2. So what we actually get is, the equation was delta G is equals to n delta H F1V minus T delta S configurational. So after substitution, we get delta G equals to n delta H F 1v minus T into minus nk ln x1v. Okay, so this becomes delta G is equals to n delta HF 1v plus nkt ln x1v. Okay, so this is the expression for change in Gibbs free energy when n mono vacancies are introduced. Now when this Gibbs free energy will be minimum, so for minimum of Gibbs free energy, for minimum Gibbs free energy, so we have to differentiate it with respect to the number of vacancies. So it will be del of delta G by del N, and that should be equal to 0 for minimum. So differentiating this equation 11 after substitution from equation 9, so differentiating equation 11 after substitution from equation 9, we get, so it becomes del of delta G by del N is equals to del of del by del N into n delta HF 1v minus T delta S, and that delta S is KB capital N ln n plus n by n plus small n ln n plus n by small n. Okay, so we get, after differentiation with respect to n or the number of vacancies, we get delta HF 1v minus TKB. So this becomes for ln n, so it becomes n into 1 by n plus n by n. Okay, into 1 by n. Okay, into 1 by n plus, for this second term it is by parts. So first we'll differentiate, this is suppose the first function and this is suppose the second one. So let us differentiate first. So differential of n is 1 and second remains constant, so it will be ln n plus n by n plus n. For ln, the differential will be 1 by n plus n by n into minus n by n square, minus n by n square. Okay, so once we have this expression, let us cancel out the terms that can be cancelled. So from here we can cancel out these n, this n and this n, and from here we can cancel out these small n's. Okay, So finally what we are left with is del of delta G by del of N is equals to del HF 1V minus kBT into N by N plus N minus kBT, so this is kBT, okay, into ln N plus N by N into plus N by N plus N into kBT. So everywhere where there is K, it is kB or the Boltzmann constant. I have moved to kB term unknowingly. So please make sure that the above K is also the same as kB and it is Boltzmann constant. Okay. So now for this, since this is almost equivalent to N, this cancels out. This is equivalent to, and this is also equivalent to N, so this also cancels out. This is also equivalent to N. So what we are left with, del of delta G by del of N is equals to delta HF 1V minus kBT minus kBT ln capital N by small n plus kBT. So these kBTs and kBTs also cancels out and we are left with only two terms now. So this is del of delta G by del N is equals to delta HF 1V minus kBT ln capital N by small n. So we reverse this ratio, so we introduce a minus sign. So this equation becomes plus kBT ln small n by capital N. So this can be written as x1v or fraction of mono vacancies. So del of delta G by del of N is equals to delta HF 1v plus kBT ln x1v, and this is equals to 0. So from here we can have ln of x1v is equals to minus delta HF 1v by kBT. So x1v is equals to exponential of minus delta HF1v by kBT. So this is the equilibrium fraction of mono vacancies. Okay, when entropy of formation is 0. Okay, so what happens if delta SF for one vacancy is not equal to 0? Then our delta HF 1V that we had term, this term is replaced by delta HF 1V minus T delta SF 1V. Then this equilibrium concentration or equilibrium fraction of mono vacancies equation would look like x1v is equals to exponential minus delta HF1V by kBT into exponential delta SF1V by kB. So these are the two equilibrium fractions of mono vacancies. So let us have a look at the curve as well. So this is your energy axis and this is your number of mono vacancies. Okay, so the variation of delta H is linear. So this is n delta HF 1V. Okay, it increases with increase in number of vacancies, and this curve is for minus T delta S. This is minus T delta S configurational. So when we club these two or add to have Gibbs free energy, that is delta G is equals to N delta HF 1V minus T delta S configurational. We have to add these two, so we get the final curve somewhere like this. So this is delta G basically. So this point, this minima, is basically what is an equilibrium or equilibrium concentration of mono vacancies. And from this graph, as you see, as these mono vacancies are increased, there is a significant drop in the Gibbs free energy. Hence, this drops brings in stability of the vacancy point defect. And okay, so that is why we term these point defects as thermodynamically stable defects. Okay, so these are thermodynamically stable defects. So these mono vacancies can also combine to form di vacancies, tri vacancies or quad vacancies as per the energy criteria. Okay, that we'll see in the upcoming lectures. Thank you.